Hi, welcome to Acid-Base Equilibrium. My name is Dr. English. Today we're going to look at an introduction to acid-base titration. Specifically, we're going to look at an introduction to acid-base titration, strong acid, strong base titrations, and calculations with strong acid, strong base titrations. Understanding the titration process. What is titration? When a solution containing a known concentration, in other words, a known molarity, of base is slowly added to an acid, or the acid is added to the base. That's basically what we're doing with titration. Acid-base indicators can be used to signal the equivalence point of a titration, and we're going to talk more about that in a little bit. A variety of indicators change color at various pH levels. A properly selected acid-base indicator can be used to visually indicate the approximate pH of a sample. An indicator is usually some weak organic acid or base dye that changes color at definite pH values. The weak acid form, HIN, will have one color, and the conjugate base, IN-, will have a different color. The weak acid equilibrium is HN, H+, IN-, where the IN is just standing for indicator. What is equivalence point? Equivalence point is the point at which stoichiometrically equivalent quantities, or 1-to-1 ratio of acid and base, have been brought together and the titration is complete. A pH titration curve is a graph of the pH as a function of the volume of the added titrant. So in this case, when we look at this graph here, we'll notice that we're starting at a low pH, so we're starting with an acid, and we're titrating it with a base. In other words, we're adding base over time, and we're seeing how the pH changes. When a strong acid, such as HCl, and a strong base, such as NaOH, are used for a titration, a pH change looks like the graph below. Prior to base being added, the pH is low. The pH is around 1. Now, where are we talking about this on this particular graph? We're talking about this location right here, where we start out with a pH a little bit below 1. As the strong base is added, the pH only slightly increases during neutralization. So now we're referring to this area right here, which is known as the buffer region. This is the point where the acid is beginning to neutralize the added base. The pH changes very quickly near the equivalence point as the titration is complete. So this point right here is known as the end point or the equivalence point. And it's at this point where our moles of hydrogen ions will equal our moles of hydroxide ions. And this is a very important thing that we're going to be looking at over the next couple of days. Continued additions of strong base is shown by the flattening of the top of the graph with a pH of 11 or 12. So this is past the equivalence point. We're referring to this point right here, where we are now dealing with a higher pH and neutralization is past completion. Calculations done with strong acid, strong base titration situations. Given the reaction, HCl plus NaOH yields NaCl and H2O. Consider the titration of 25 milliliters of 0.1 molar HCl with 0.1 molar NaOH. So let's list out our variables. Our volume of our acid is 25 milliliters. The molarity of our acid is 0.1 molar. The volume of our base is our X, that's what we're going to be looking for, and the molarity of our base is also 0.1 molar. So we can take these variables and plug them into our formula. So the molarity of the acid is 0.1 molar, the volume of our acid is 25 milliliters, the molarity of our base is also 0.1 molar, and the volume of our base is what we're looking for. So when we work this out, we find that the volume of our base is going to also be 25 milliliters, and really what we should have this in is liters, so that's going to be 0.025 liters. And this is the volume that we need to reach the equivalence point. Ultimately, what we're looking for here is an equivalent amount of moles of acid to moles of base. So if we use the molarity formula, we can say molarity is equal to moles over liters. And if we look at the molarity of our acid, we have 0.1 molar of our acid. We're solving for moles of our acid. Our volume should be in liters, so that's 0.025 liters. And if we multiply together 0.1 times 0.025 liters, we're going to get 0.0025 moles of acid. And at the equivalence point, we want that to equal 0.0025 moles of base. So at the equivalence point, that's what we're trying to look for, that the moles of acid is equal to the moles of base. And we're going to constantly, through this whole video, be referring back to our original molarity of our acid and our molarity of our bases. So as we're doing this and you're wondering where are these molarities coming from, they're coming from right at the beginning of this tutorial. So again, the equivalence point is reached when the number of moles of base added equals the number of moles of acid initially in the solution, and that's where the base is your titrant. Since the concentrations of both the acid and the base are identical, the volume of sodium hydroxide needed is the same as the volume of HCl. So now what we're going to do is we're going to look at pH over a given amount of time. So we're going to start with calculating the initial pH prior to the addition of any base. So the initial pH of the solution is simply the pH of a 0.1 molar HCl. So that means our hydrogen ion concentration is equal to 0.1 molar. And we can figure out pH by saying pH is equal to the negative log of our hydrogen ion concentration. Therefore, the negative log of 0.1 molar, which is equal to a pH of 1, which is basically what we stated at the beginning of this tutorial, that when we look at that strong acid, strong base graph, we're starting at a pH of 1. Calculating the pH after a small amount of base is added. The concentration of our hydrogen ions can be calculated anywhere on the curve prior to the equivalence point by realizing the ratio of acid to base is 1:1, otherwise known as stoichiometrically equivalent. So calculate the pH after adding 5 milliliters of sodium hydroxide. So step 1, multiply the added volume of base by the molarity of the base. This calculates the moles of base added. So we know that molarity is equal to moles over liters. The initial molarity of our base, as given at the beginning of this problem, is 0.1 molar hydroxide ions. We are solving for moles of hydroxide ions, and the amount of base that we're adding here is 5 milliliters. So we need to change that into liters, so that's 0.005 liters. So we multiply together 0.1 times 0.0005 liters, we're going to end up with 0.0005 moles of hydroxide. Step 2, subtract the moles of base added from the moles of acid present in the solution. And if you recall, at the very beginning, we calculated the moles of acid. And again, as we go through this process, we're going to be constantly referring back to that moles of acid. So before the addition of the hydroxide ions, we have 0 moles of hydroxide, and we start out with 0.0025 moles of hydrogen ions in our solution. And water's in there, but we're not going to take water into account. The addition of the hydroxide brings in 0.0005 moles of hydroxide. Now we need to neutralize that. And we're going to use some of our hydrogen ions to do that. So we're going to subtract that 0.0005 moles of hydroxide from our original 0.0025 moles of hydrogen ions. As a result, our base will be neutralized, and we are left with 0.002 moles of hydrogen ions. And ultimately, this is going to affect our pH. Step 3. The hydrogen ion concentration can then be calculated by dividing the number of moles of hydrogen remaining by the total volume, initial plus added volume. And this is a key step here. So we have 0.002 moles of hydrogen ions remaining after we removed those hydroxide ions to neutralize it. We added 0.005 liters, and that came from the volume of the base. And we need to add that to our original volume of acid, so 0.025 liters. So that is the volume of acid that I started with. So that means I'm going to have 0.002 moles of hydrogen ions divided by 0.03 liters of total solution. So this is my total volume. And when I work this out, my new molarity for my hydrogen ions will be 0.0667 molar H plus 1. So that is the molarity after we have neutralized that addition of the 5 milliliters of the sodium hydroxide. The pH can then be calculated reflecting the addition of the base. So we know pH is equal to the negative log of my hydrogen ions. So negative log of this new molarity of my hydrogen, 0.0667 molar. And when I work this out, my new pH is 1.18. So in this case, the pH has increased from 1 to 1.18 due to the 5 milliliter sodium hydroxide addition. In general, for reactions of strong acids and strong bases, before the equivalence point, the hydrogen ion concentration and therefore pH can be found by dividing the number of moles of hydrogen ions remaining by the total volume of solution. Now let's calculate the pH after adding 15 milliliters of sodium hydroxide. So again, just like we did before, we need to figure out how many moles of sodium hydroxide do we have to work with here. So molarity is equal to moles over liters. The original molarity that I started with at the beginning of the problem is 0.1 molar NaOH. So 0.1 molar NaOH, which is really just the hydroxide ions. We are solving for moles of hydroxide. My volume now has changed from 5 milliliters to 15 milliliters. So on the bottom, I'm going to put 0.015 liters. I'm going to cross multiply here, and I'm going to get 0.0015 moles of hydroxide ions. Step 2, before the addition of the hydroxide, I'm going to have 0 of this. I start out with my original amount of hydrogen ions. Always go back to the original. So 0.0025 molar of my hydrogen ions. I'm not going to worry about the water. The addition of the hydroxide means that I am adding 0.0015 moles of OH here. I need to subtract that from my existing amount of hydrogen ions, so subtracting it, so 0.0015 moles. This should really be moles, not molarity. As a result, my moles of hydroxide ions are neutralized. And how many moles of hydrogen ions do I have remaining? Well, I have 0.001 mole hydrogen ion remaining. And from that now, I need to figure out how my molarity has changed. So step 3 is going to take that remaining hydrogen ions, so 0.001 moles of hydrogen ions, and I'm going to divide that by my total volume. So I have 0.015 liters, and that's coming from the added base. And I'm going to add that to the initial volume of acid that I started with, 0.025 liters. So that is for my original volume of my acid. I'm going to have 0.001 moles of hydrogen ions over the total volume. And if I add those two numbers together, I'm going to get 0.04 liters. So again, that is my total volume. And if I divide 0.001 by 0.04 liters, I'm going to get a molarity of 0.25 molar H plus 1. My final step is to take that molarity of hydrogen ions and see how it translates into a pH. pH is equal to the negative log of my hydrogen ions, negative log of 0.025 molar. And when I work this out, my new pH is now 1.6. So as I add this base over time, my pH is slowly increasing until we reach the equivalence point, which in this case, for a strong acid, strong base situation, the equivalence point is going to be at a pH of 7. Let's look at a situation where we calculate the pH after the equivalence point, where the hydroxide ion is in excess. As sodium hydroxide is added beyond the equivalence point, it becomes the excess reagent. The amount of hydroxide ions in excess can be calculated by subtracting the initial amount of hydronium ions from the amount of hydroxide ions added. Calculate the pH after adding 30 milliliters of sodium hydroxide. Step 1. Multiply the added volume of base by the molarity of the base. This calculates the moles of base added. And this is what we've been doing in step 1 all the way through. So we always start with the molarity formula. Molarity is equal to moles over liters. The molarity of my base is the same as it's been since the beginning. So 0.1 molar hydroxide. We are calculating moles of hydroxide. But now my volume is 30 milliliters. So we need to change that into liters. So that's going to be 0.03 liters. If we cross multiply here, we're going to get 0.003 moles of hydroxide ions in solution. Step 2, subtract the moles of acid present from the moles of base added in solution. So we just calculated that we are working with 0.003 moles of hydroxide ions, and we're going to subtract 0.0025 moles of our acid, which we originally started with. This was our original. That was the maximum amount of hydrogen ions that we had in the solution. So if we subtract those two, we find that we have 5 times 10 to the negative 4 moles of hydroxide ions in excess. So we have neutralized all of the original acid and we have hydroxide ions left over. So this calculated amount is the moles of hydroxide ions in excess. Step 3. The hydroxide ion concentration can then be calculated by dividing the number of moles of hydroxide remaining by the total volume, initial plus added volume. So the amount of hydroxide ions left over is 0.0005 moles of hydroxide ions. We added in 0.03 liters of our base, so that's hydroxide ion volume right there, to our original volume of acid, which is 0.025 liters. So that was our original volume of H plus 1. If we add those up, we get 0.0005 moles of hydroxide over a total volume of 0.055 liters. If we divide those two out, we have 0.0091 molarity hydroxide ions. So this is the molarity in excess after the neutralization of the acid. Step 4. The pH can then be calculated by using Kw to find hydrogen ion concentration and then pH. So we know that Kw is equal to hydrogen ion concentration times hydroxide ion concentration. So to find hydrogen ion concentration, we're going to take Kw and we're going to divide it by our molarity of our hydroxide ions. So in this case, it's going to be H plus 1. Kw we know is 1 times 10 to the negative 14. Our hydroxide ion concentration that we calculated back in step 3 is 0.0091. And if we work that out, we get a hydrogen ion concentration of 1.1 times 10 to the negative 12. We can then take pH is equal to the negative log of my hydrogen ion concentration, negative log of 1.1 times 10 to the negative 12. And then we could calculate pH and find out that it's 11.95, or we could just round it up to 12. So in general, for reactions of strong acids and strong bases, after the equivalence point, the hydroxide ion concentration and therefore the pOH can be found by dividing the number of moles of hydroxide ions remaining by the total volume of solution. The hydrogen ion concentration is found by using Kw. Let's look at one last example. Calculate the pH after adding 40 milliliters of sodium hydroxide. So again, we always need to start out by saying molarity is equal to moles over liters. Our original molarity of our base is 0.1 molar. We're solving for moles of hydroxide, and our volume here is 0.04 liters. So if we work this out, we're going to have 0.004 moles of hydroxide ions. So there's our step 1. Our next thing that we need to do is take 0.004 moles of hydroxide ions and subtract it from our original moles of acid. So 0.0025 moles of hydrogen ions to see how much hydroxide ions we have in excess. So that would be 0.0015 moles of OH minus in excess. Now that we have that, we can take that number of moles of hydroxide ions, 0.0015 moles of hydroxide ions, and we can say, well, we had a volume of 0.04 liters of base. Add that to our original volume of acid, which is 0.025 liters, 0.0015 moles hydroxide ions. Subtract that from the total volume of the base, which is going to be 0.065 liters. Divide those together and find our new molarity, which is 0.023 molar hydroxide ions. Again, we can take the Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. We can solve for hydrogen ion concentration, Kw OH minus 1. Kw 1 times 10 to the negative 14. The hydroxide ion concentration we calculated is 0.023 molar. So our hydrogen ion concentration here is going to be 4.3 times 10 to the negative 13 hydrogen ions. And finally, we can calculate pH. pH is equal to the negative log of our hydrogen ion concentration. We can plug that in and finally solve for our pH, which will be 12.36. So what we've done here is looked at how the pH has changed over time, starting with an acidic solution and slowly adding different volumes of base. So what did you learn? We looked at an introduction to acid-base titration. We talked about strong acid, strong base titrations, and then we did a bunch of calculations with strong acid, strong base titrations. Need more help? Feel free to contact me. Have a great day.